Section 6.8, proof by mathematical induction. So here's a question. What's the sum of the first n odd numbers? Odd natural numbers. Natural numbers are your counting numbers. We start at 1, 2, 3, 4, all the things you can count. Okay, so what I'm going to do first is I'm going to try this out. I'm going to say if I have one natural number, I just have 1, and its sum is 1. If I have two numbers, two of the natural odd numbers, I have 1 and 3. My sum is 4. I'm going to continue on. 1, 3, and 5 is going to be 1, 3, and 5 is 9. If I have 1, 3, 5, and 7, I get 16, and some of you might see a pattern already. I keep going. 1, 3, 5, 7, 9. 16 plus 9, or sorry, 16, yeah, plus 9 is 25, and then I get 36. So some of you will notice that these are all perfect squares. So it seems like if I had n natural numbers, just like if I had 6 natural odd numbers, it's 6 squared, it would seem like it would go to n squared. But that's not a proof. That is not inductive reasoning, that's deductive reasoning, okay? Or sorry, that is a pattern, okay? We just saw a pattern, but we want to prove it for real. And the way we prove it, the steps in mathematical induction, is it is true for the first few natural numbers. So we check it out, we say, yeah, that looks right. Then we assume it's true for all natural numbers, k. Then, if this assumption is true, we can prove it's true for the next natural number, k plus 1, then it has to be true for all. So we say, okay, let's say it's true for all numbers. Now I'm going to prove it's true for all numbers plus another one. Okay, so let's go through a sample of a proof. Use the principle of mathematical induction to prove that for all natural numbers n, 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4. Continue on in this pattern. 1 over n plus n plus 1 is equal to n over n plus 1. So let's see if we can prove that. So first of all, let's check it for a couple numbers. Does that work for 1? Well, 1 over 1 plus 2 does equal 1 over 2. Okay, so it works for the first one. Now, let's see if it works for the second one. 1 over 1 times 2 plus 1 over 2 times 3. That is equal to, does that equal 2 over 2 plus 1? Does that equal 2/3? Well, this is 1/2, this is 1/6. If I added those together, I got a common denominator. Yep, that would work. Okay, 2/3 is equal to 2/3. Because this is a 6, that would be 3/6, so we'd have 4/6, which is the same as 2/3. Okay, now what we need to do is we need to assume it's true for n equals k. K is a natural number. So I'm saying this is true. I'm assuming that to be true. Now, if n equals k plus 1, if I can show that that is true as well, then I have proven this. So I have 1/2 plus 1 over 2 plus 3 plus all the way, and then I add one more case. K plus 1, k plus 2. Does that equal to k plus 1 over k plus 2? So take a second and scroll back if that doesn't make sense. So I just went 1 more than k, 1 more than k plus 1. That's all I did. This is all the same. So this part in red is already true. That part is true. Okay, and that is actually, I showed, was equal to up here, k plus k plus 1. Okay, so really this can be simplified into that. Now making a common denominator and adding this together, I get k squared plus 2k plus 1. I factor the top, I cross out common factors, and I have indeed shown that they are the same thing. Okay, so finally I'm going to say it must be true for all natural numbers. Okay, take a second and look back at our rules, what we did. First of all, we checked it's true for the first numbers. We showed it was true for 1 and 2. Then we're going to assume it's true for all. And then, based on that assumption, if we can prove it's true for one more number, then it's assumed to be true. Use the principle of mathematical induction to prove that 2n plus 1 is less than 3n for all natural numbers such that n is greater than 2. First of all, we're going to see it works for the first couple numbers. Well, I said it had to be greater than 2. So, well, 2 cubed is less than 3 squared. Yeah, 8 is less than 9. 2 to the 4th, so that would be 8 times 2, 16 is less than 9 times 3, 36. Yep, that's true. So now I'm assuming it's true for n equals k with those stipulations. I'm assuming that to be true. Okay, now I want to show it's true for k plus 1. So what I do is wherever I see k, I put k plus 1. So k plus 1 plus 1, in other words, k plus 2, and k plus 1. I need to show that's true. Well, using exponents law, 2k plus 2 is the same as 2k times 2 squared. And this is the same as 3k times 3. I could rewrite that as 2k plus 1, because 2 is just 2 times 2. So I could write that as 2k plus 1, and I could write that as 3k. Okay, and now you'll notice 2k plus 1 is less than 3k. 2k plus 1 is less than 3k, and 2 is less than 3. So if something less than something else, and I'm multiplying it by something smaller on this side and bigger on that side, it must be true. Okay? And that is the concept here.